I'm only going to talk for 5 minutes because we know we can't tell Peder to talk for 5 minutes. And then after that, Peder's going to talk about something which is really interesting, which is some modeling software that can be used for doing some work looking at mosquito data and habitat data and land cover data. And I think this is going to be really a fun talk today. We have a follow-up talk that Cassie is going to put into the calendar, and it's Dr. Mike Wimberly, who is a NASA scientist who is working with mosquitoes in space to do risk maps of vector-borne disease. Thank you very much. Haven't finished my first coffee yet, so he gave such a great talk last spring that he can't possibly improve on it. So we thought we would just show you that video. It's about 35 or 40 minutes long, but that way you can get, once you have learned more about the tools here, you can then go back and watch his video. I think it'll make a lot of sense to you. So, okay, without further ado, I want to talk briefly about the Earth system. And this is just to sort of give a background for where Peder is going. So the Earth system is it's like the central dogma in biology. It is the way that scientists who work with Earth and space science think about the world. And to sort of move forward, it's like the Earth system science is something that began to happen right when I was finishing, when I was in graduate school, where before that we had people that were biologists and people that were hard rock geologists and people that were ocean scientists and people that were atmospheric scientists. And what began to happen, like in the 1990s, early 1990s, late 1980s, was that research began to happen. And what they began to see is some of the most exciting questions were at the edges of each of those interactions. So for instance, how does land cover affect precipitation? How does atmosphere affect biosphere, and so on and so forth? And we began to get really interested in this kind of connection because this is when computer modeling was starting. That started like in the mid 70s, but really came into its own in the late 1980s and 90s. So when we say, what is Earth system science? I love this thing that Leonardo da Vinci said: realize that everything is connected to everything else. That is our mantra. I'm going to make this slide set available to you because we're not going to do the whole thing. But what's really important, is before, people studied to be a biologist or a geologist and they were in their departments. And nowadays there are Earth system science departments that have all those together. So we've gotten out of those stovepipes and we're talking to each other. This was really only possible because we had a new view of the world. And we talk about the beginning of Earth system science going back to space science, where we had some astronauts were taking photographs of the Earth from space in 1972. And this picture became really famous. It was called the Blue Marble. And it was just exactly what science needed for us to begin to think about how we're all connected. You can see here how the ocean's life, land and atmosphere, ice, they're all connected. And so this stimulated what we call a paradigm shift in thinking. And it's because of this shift in thinking that I got very interested in Earth system science. I was never a rock person. So anyway, so what we do with Earth system science is we're looking at different spatial scales of analysis. So you might set up a terrarium and look at how you put some water in the terrarium, some soil and some plants, and then you close the bottle and you've got a system which is all separated from the rest of the world. So that's a system that you could study experimentally. but you can also do what we're doing with the land cover tool. You can look at things in a 100 by 100 meter square. You can look at things from satellite imagery. You can look at the whole world. And then this is just what Leonardo da Vinci said: change happens in all directions. Everything is connected to everything else. And so here is it gets really complex. You don't need to know these things yet, although they are included in many models. But basically, we talk about fluxes, which are changes, and the changes sometimes have feedback loops. So if you have a change that happens in the biosphere and it actually impacts the hydrosphere will it's back at you. It will also impact the biosphere again, and then begin to look at all the different parts, and you suddenly have something very complex. So it's these complex relationships that we're trying to get at when we use models like random forest. And what we do is we take the observations that we're making with our eyes as remote sensors and our cameras, and we change those things that we see into numbers. And then we use those numbers to begin to understand how one part impacts another part. And so Peder said, when you talk about this, make sure you show a carbon diagram. So here is an example of this. You might have seen this in a textbook that you've had in school, but we use the carbon diagram to better understand Earth systems. And all you can see here is that you can see that carbon comes from plants. It then becomes rocks. The plants produce CO2, which goes into the atmosphere. The atmosphere has a feedback loop where it then begins to trap some of the energy in the atmosphere, and it stays a little bit longer than it should. And then that is what causes the warming that we're seeing on our planet. So you can look at one of these diagrams and really begin to understand how incredibly complex this is, and that what's happened in what we call the Anthropocene, which is today, the time where human impacts are been elevated to having the same kind of effect as a lot of these natural features, that people, our buildings, all the cement that we've made that's off-gassing CO2, fossil fuel emissions, these are all things that are changing our atmosphere and impacting our entire Earth system. So we'll put this up for you to take a look at. It's a fun little tutorial that, there's nothing you have to do except watch it, but it helps you to build that Earth system thinking that just takes a little bit of practice. So that's what I wanted to show you today without going into it in great detail, because I actually think that what Peder is going to be talking about is a lot more interesting than this. So without further ado, I'm going to pass the mic on to Peder. And if you have any questions, go ahead and put them in the chat, and I will be answering questions in the chat as Peder just drones on about science.
Well, Rusty, I love the image that you had up there. Satellite images right in my backyard, which was the big landscape change of Mount St. Helens, of that volcano erupting and the after effects of that. So I know you didn't plan that, but I just appreciate it when.
Well, I didn't plan that one, but I did plan to go to a picture of landscape just for you.
Exactly, I appreciate that.
Okay.
So thank you, everyone, for coming this morning to hear a little bit about, I think, something that will help you with your projects. And this is, we've had some questions talking about numbers. How do you format data? How do you actually start running some of these models that people talk about? And so today I wanted to demystify this a little bit and give you some tools. And it's actually really interesting timing right now, because NASA's training program, the Applied Research Sciences Center, actually RSET is the acronym. They are having a training right now on using Google's Earth Engine to monitor land cover from space. And so they are providing us some real-time training data And so I wanted to kind of highlight that, this is something that scientists are constantly doing, which is updating their methods, updating their data. And so, this is one of these things that, just kind of recognize that what we're going to present to you today is really kind of cutting edge, and NASA's trying to teach their people, their scientists, how to use these tools. So what you guys think about or the way you approach it is pretty novel, and so I just want to start with that piece of things. And luckily, there's lots of resources out there. I'm a resource. Rusty's a resource. The people in this, here on this call and in our learning community are all resources. Mateo, is a great resource. He's done some of this modeling, predictions using the land cover data that we're all collecting, some satellite data. And so we have a lot of resources here, as well as, online tutorials. So I just wanted to mention that science is changing right now because of cloud computing and our access to all this satellite data. So what we learn and the way that we approach things today is going to change, because hopefully we'll solve some problems. And I want you guys to be part of that problem solving. So as we think about our information, this is one of the key things that we do together as a community, right? Is we actually create data. And managing that data is one of the things that we have to think about, because it's how we build an algorithm to access that information. It's how we access the satellite measurements, like the ones that are behind me today. And so this data, we really want to be thinking of as something that we can use today, but we also want to be thinking about how to store it, how to capture it, and how to describe it so that it can be reused in the future. Because science is all about creating data and information, processing that, providing some results, but hopefully giving it to somebody else so that they can repeat that process over again. This search and research idea, right? So even when you're thinking about your ideas and somebody has made a model, and you'll hear that term a lot. If somebody's made a model somewhere, a question I always have is, does that apply to my area? Like what Rusty was talking about, somebody makes a model, like Dr. Mike Wimberly, he makes a model for a particular area in Oklahoma where he's located, where he's collected some data. Maybe that's where the data is available, and nobody was collecting it elsewhere.
And
Well,
I also want to say too, is that when you set up traps, you set up 3 traps.
mm-hmm.
You have created a model of a mosquito landscape, a very, very simple model. The same thing about setting up a terrarium in a pot bottle. That is a physical model. And
Yeah.
so we're going to be talking here about number models. So
Yeah.
I just wanted to point that out, because they've already been modeling, Peder.
Right, exactly. And so, this idea of a model is simplifying the landscape to the important pieces. That's essentially it, right? And so, when somebody makes a model or tries to predict where they're going to find mosquito habitat, it could be a mental model, just something in your head that you recognize. If I go near this feature or near this area, this is going to happen. You have that mental model, right? You have a physical model, like what Rusty was talking about, where you actually have sometimes miniature pieces or smaller pieces, or you are trying to simplify the landscape and trying to manipulate it, right? And so we try to do the same thing with Earth. And so this is where we have Google Earth. We have a lot of the atmospheric data, talking about clouds, like what's behind me, vegetation, green things like that on the surface of the Earth. All of that is data, sometimes measurements, and sometimes modeled information, right? And so this is where actually looking and reading what people have are how they're describing their information is really key here. Okay, so and people spend all their time just going through this managing data cycle. Sometimes they're acquiring data, like what we're doing. Sometimes somebody will process that data, and they'll spend their time just looking through what somebody has acquired. Other times there will be an analyst, and they will actually spend their time working through trying to predict, use those observations and predict where they might find other species or other habitat, or other things into the future, future scenarios. um, Sharing the data. Now, this is an interesting one where we want to be thinking about where we put our data, where you might find your data. Just because data is out there doesn't mean that you should trust it, right? And so learning who to trust is really important when you think about your science data. If you're going to be especially relying on that in your models, you want to be really sure that the person that created that did a good job. And so where you get your data is really important. And so we have ideas and locations that we use as scientists. NASA is one of those trusted sources for a lot of us. They have the raw data, the authoritative data, that you can use. And sometimes you can find the satellite data elsewhere. Other companies might download it, and they might make a version available. I be suspect of that, because they might have manipulated the data in a way that isn't the actual measurements that were made from space. So just be aware of where you get your data from, and if this is a place that your mentors and we can help guide you to trusted sources as well. And then thinking about that preservation of your data. Again, this kind of gets into some of the formats that you have to deal with. We've been talking a lot about a CSV file, comma separated values. That's a generic text format that allows us to easily share information across different platforms, like whether you're working on a Mac computer, or whether you're working on a Windows computer, or working on a Linux or Unix computer, or some other formula. And so again, I just kind of raise this because you will come across a lot of different formats of data, and we want to be thinking about ones that are open and that are can be read into the future. Okay, so if you have any questions about the data formats when you're looking or trying to find data, let us know, and we can help decipher that. A lot of the data that you'll find from NASA is in what is known as open format. So those are things like a comma separated file. You don't need any special software to read it. And that's one of those things that we want to think about when you're coming up with your project idea. Is there's a lot of great software and tools that are out there, but they can cost a lot of money. And so in science, that sometimes gets in the way. And so we have to make a call between whether to pay $10,000 for some software to get something done really fast, or is that something that we need to build ourselves so that we know what's in the algorithms in each one of the steps of the process. So all of that, it goes into this managing our data and thinking about our data long term. So I've thrown out a couple ideas there, but I want to take us to looking at some satellite data, because this is where we're getting really interesting insights. I mean, Rusty started us off thinking about Earth as a system. Well, Earth as a system is really put together by these measurements that are made not just in one location, but literally across the globe. And one thing that I find interesting and useful when I think about science is that we found out that the Earth was round by measuring the shadow length at different places around the world. Well, that individual measurement meant something to that individual person, but it wasn't until all of those measurements were co-located together into a library in Alexandria in Egypt, and somebody took the time to go through them, organize them, and do some summaries around them. And that's when this pattern emerged that at areas that are higher latitude, have higher latitude numbers, there was a longer and shorter change in the length of shadows. And so, again, this demonstrates that there can be these observations that are made, but the meaning of them, it doesn't get revealed until somebody else comes along and processes them and organizes them and reduces those thousands of measurements into one number or maybe two numbers. Okay, so you can see that NASA here has all of these different types of data sets. Sometimes they're actual direct measurements, like a reflectance, surface reflectance. So is the sunlight bouncing? How intense is that sunlight bouncing off the surface of the Earth? Other times it's actually modeled information, or like what is the extent of human buildings on Earth? Okay, we haven't actually counted every single one of those buildings. We have a limitation in our measurements from space. We have our lack of training data, and we have things that get confusing, like when trees are over the top of buildings. Maybe we can't see those from space. So you see that there's all of this information that NASA has, and some again are measured and put together with physics. Others are modeled. Others, even the precipitation estimations, those are models, and so they're not actual true measurements. Right. So again, I wanted to just kind of highlight this because this is an example of one of these places where you can go and explore the different data sets that are available as you start thinking about the data or information you might need to predict where mosquito habitat might be, or where you might actually have good water for drinking or playing in, or other things like that. So, if you haven't seen it yet, go to this Worldview website. There's some really great data and information there put together in these different themes. But I wanted to highlight a little bit of the raw data behind it. Right, we have the satellite data. And one of the things that gets presented a lot is this nice cloud-free view of Earth, right? Well, that's not really the case. In most of the time, we're trying to see through those clouds. So a great question when we're thinking about the Earth system is, how cloudy is your location? This is one of these nice things that we can actually see from space. And so, the first thing that a land system scientist would do is try to get rid of these clouds, or identify how much of the atmosphere is cloudy. And so, we do this simply by highlighting areas that look like clouds. And so I'm going to pause right here and ask the question, how do you identify clouds? And I'd like somebody to speak up here. Yeah, Nicole, I see your hand up.
I mean, typically they're gonna be white and kind of like fluffy looking.
Yeah. Okay. So you have two. You brought up at least two characteristics there, right? So this is the model piece that we're trying to do, right? You have you've been trained, or you have the image in your mind of what a cloud is, at least from the ground, right? And so we're applying that to this satellite data here. And you're exactly right. We have a color that we're looking for. And then we also have this texture, and you kind of highlighted sort of a puffy feature to it. And we can see some of these puffy, things that are in this satellite image. So great, yeah. So Nicole, we'd want to look for things that are white and puffy. So we have a texture and a color. Nandini, I see your hand up.
Yeah, I think we can use like infrared imagery from the satellite, and that can detect the temperature of like the cloud surface, like the top maybe, and that's an identifying characteristic. And then maybe like also using that get information about its texture, like Nicole was saying.
Yeah, those are all really great ideas. And so you hit on something that was really important here about satellite imagery versus almost anything, all other types of data. We usually have this natural color, the red, green, blue wavelengths, and that's why things look the way that it does. But then with satellite data, we can usually measure beyond that. And so you hit on it exactly right, that if we move beyond what we usually see here, we might get some additional information that can help us discriminate, especially those cloud edges from the land, right? Like, the really bright centers might be really easy to identify, but how do those edges where you have the cloud shadow ends, and then you have ground or some water vapor, right? That's usually where we have the error in our model. Trying to detect that edge is a limitation in most cases for our modeling. So those are all great ideas. Maria.
You could also, like, if you have photographs from kind of like several days or hours before in the same geographical region, then you can look at changes, because clouds are probably going to change faster than anything else.
Yeah, so you hit on another really important piece when we think about models is the temporal aspect. So you guys did a great job of hitting on the temporal aspect to what we're actually trying to model. Are we trying to model something on a daily basis, meaning that we then have to have measurements on a daily basis, or are we measuring something on a monthly basis where we can where we're averaging across those 30 days, or is it something that we're looking at a yearly time step? So thinking about that time piece is really important, so that you capture the phenomena, right, that you're trying to actually see, as well as be able to use the power of statistics and the power of numbers, right, to reduce some of that uncertainty that might be there. And so you're exactly right, Maria. If we actually just switch days, we can actually see that here we have a much more cloud-free image. And so one easy way of trying to detect clouds that we've done, that some people have used, is to just have a more cloud-free image and just literally subtract those digital numbers from your cloudy image. And so a model, that would, that great variation would help us to detect those areas that are more likely to be clouds, because they have a big difference between them, right? And so, just a simple subtraction, again, it can be a simple mathematical way to do a data reduction, or to identify features on that landscape. Again, we always want to be thinking about the resolution of our imagery. And this is one of those differences that hopefully you're all familiar with. As we think about our Globe Observer photos, somebody has one version of an iPhone and another person has another version of an iPhone, you can end up with some very different image resolutions. And so with our satellites, we have the same kind of thing that's happening. We have different image resolutions that allow us to see different things, and can discriminate our objects a little bit better. So there was one view of kind of the landscape. We have another satellite that the European Space Agency has put up. And this one, you can see that we have several more spectral measurements. So we can use that additional information, hopefully, to help us to identify here that, they did some weird kind of funky things. This is where every satellite image is actually composed of individual band measurements. And so we can do things where we can put together what's known as this false color, because we can only really show 3 things at a time. This is the limitation of our computers. All right. And so you can see that I can make total gibberish, right, with these measurements. But the key is that we have all of this information to work with. We have these multiple bands. And so the nice thing is we have the computers that can do all of the hard math for us. And so, when you're thinking about your projects, don't necessarily get hung up with not knowing how all of these algorithms might work or how these classifiers might work. Sometimes, one of the interesting things is just putting the data in and seeing what the results come out as. And here we can start to see some interesting patterns emerge, right? But what do they actually mean? And this is where we need that ground information that you guys are collecting to make some sense out of this. And if we zoom in on this particular area, we have some context from some other data, right? Some other information. And so, this is that piece that now with our models, we can start bringing together not just one layer of information, remote sensing from a satellite, but in fact, we can sometimes bring together other data. In this case, text labels. And so, so we can start bringing together this different spatial data, right? So when we think about spatial data, think about 4 things. We have points, like locations here, like that tells us this city exists at this location or this house is at this location. We have lines, which connect 2 points together, or we have polygons. And then, and that's just 3 points that connect together. And so that's the way that when you start making a map, like we did yesterday in the Meetup and Do Science, or we'll be doing later today in our Meetup and Do Science, those representations are what we are actually using when we make a model on a map, do this spatial modeling. And then we have those pixels, the rasters. And so the key here is we just want to be thinking about what we're representing on the landscape. And then we have to format it. We have to kind of put it together into something that a computer can work with and a computer can read. Okay. So I wanted to just kind of highlight that sometimes just playing around with these different measurements and some of the different data layers can lead you to some interesting results, right? So when we start thinking about our actually applying and doing land classification using all of this data that we're putting together as our team, one of the keys is remembering that we're not the first people to do this. And so we have some other information to be able to draw upon or to be able to compare ourselves to. Again, these land cover types have some error associated with them. And that's one reason why we're not only going through and doing those ground photos that we can use to compare to a model, in this case, this land cover map, but also where we can use that to inform any models that other people on our team are creating. And I'll describe that a little bit further. Again, one of the things that we have the opportunity to do is think about pixels just by themselves, those spectral measurements. You know, Nandini, you nailed it exactly. Like that's each one of these pixels, which can be 10 meters, it can be 30 meters, it can be 500 meters. You know, that's just what the satellite is measuring. It's measuring the light reflecting and on a pixel basis like that. So we can work on those pixels, and that there's some information there. But also, you know, like Nicole highlighted, you know, those objects, that puffiness of those clouds, that also gives us some useful information. And so, you know, exploring the different results between pixel-based or object-based is an area of research right now. So that might be a really interesting project for you to consider. You know, one of the keys is that when we think about those pixels, Nandini, you really hit it, and I'm picking on you a little because you're right there in my screen. So sorry about that. But you know, the different features on Earth, whether it's buildings or whether it's soil or water or vegetation, will reflect sunlight differently. And that's one reason why, you know, the satellite image behind me kind of has the colors that it does, is because of what's reflecting behind it. And so we can use that, those spectral signatures are what they're called, to help us to actually distinguish between something like vegetation and soil. And this is something that you guys have heard a lot about. So it shouldn't be anything brand new in this way. But I want to really kind of highlight that because it's these distinctions that allow us to make a map, that allow us to highlight, to calculate the amount of area that is vegetated or has soil. And if we compare that to where we're finding our mosquito and map that over a graph like this, we might find that all of our mosquitoes are in this vegetation area and we're not finding any in the soil area. So a really simple habitat model is just show me all of the pixels that are vegetated, right? So it can be that simple to make a model to identify other mosquito habitat like that. And that's where these land cover classifications come in, but there's limitations because you have to have a very particular definition of what a grassland is, or what a tree is. Does a tree have to meet a certain height? Does it have to be of a certain species? You as the researcher have to be very specific about that. And that will lead you into deciding whether you want to let the numbers kind of group themselves, or whether you're going to guide that through a supervised classification. And so, there's good reasons to do one versus the other. But just to kind of recognize that, in each case, we need to know what's on the ground. So again, this kind of leads us to why we're collecting our Globe Observer photos in the way that we are, is to be able to have training or testing data running a supervised or unsupervised classification. And so, the overall workflow for a project like this is very similar. But the big difference is that you spend a little bit more time with the supervised classification, gathering your information that you know about. And again, this is where what you're doing with your photos can be training data for a supervised classification. When you do that, you want to look at the results of what you collected. And so you might make a graph of this, and it might look very similar to this right here, where you can see that 10 of your observations group together as vegetation. 10 of your other ones group together as soil. Right. So doing that grouping helps you to know the variation of your of the date of the training that we have to work with. And this is where you individually in your 36 points in your area of interest may not have a lot of variation. But this is where teaming up with somebody else might allow you to pool those together and actually have some variation in your training data. Again, this goes back to what is it you're trying to predict, right? So we talked a lot about mosquito habitat, but you can also try to predict the land cover that's at that location, right? And using that satellite data as your input. And so, you know, that's a lot of times what we're doing. We go out and we sample a couple locations. We look for similarities and differences. And then we will say, you know, to the computer, go find me all the other pixels that look like this one. And then we'll evaluate those results. So that's a typical workflow for building a model. Again, you might spend a lot of time kind of sifting through these at the very beginning, but that's overall what would be your approach. The key is, what are those inputs that are going in? And this is where the selection of your satellite imagery, it might be cloud covered, so you might have to pick a different satellite, or you might have to average observations to get around your clouds. You know, this can take a little bit of time to kind of figure out your inputs and what are good for your particular area to identify the type of features you're after. So in this case, you know, we're looking for conifer, water, and deciduous. And you notice the trees both kind of have a similar green signal, kind of similar to what's behind me. You know, trees are vegetating and reflecting that green light. So we can use that to identify or hopefully identify those areas that are doing that. Now, you've heard a lot about this term machine learning, right? Or AI, artificial intelligence. And the thing is, like, we've been doing classification, we've been using machine learning since we've had computers. It's really not anything new. It's just the way that we might package them, or the way that we might use hundreds of computers now to do some of this. But we still understand what's sort of happening in this black box. But it can be really complex. And so now a lot of times we will run something through this black box, and we'll spend a lot of time looking at the outputs. What did this give us? Does it make sense? Does it reveal some new patterns? So it's kind of your hypothesis is not necessarily as upfront as when you're doing a chemistry experiment or something like that. Sometimes you are just putting data in and saying, how does it cluster together, or how does it group together? And then what does that tell me about the landscape or the world around me? So, you know, one of the keys is that there's a lot of classification algorithms out there. Again, you know, I think one of the interesting activities is seeing what the results are of running one or two of these classifiers on the same data set. Do you get the same results, or are they different? And where are they different? Just describing that is a really good activity, because each one of these classifications, you know, has its strengths and it has its weaknesses as well. And so that just finding out those results might be a really good approach. And here I'm showing you Google's Earth Engine. And I'm highlighting this because this is a pretty powerful tool that gives us the ability to share algorithms. Almost all of the satellite data is available on Google's servers. They're making a copy. So we trust them, but yet we like to verify what they come out with and what they do. But we have a lot of satellite data. So if you're thinking about modeling or wanting to do something with satellite data, this might be a really good option to consider. And like I said, this is exactly what NASA's applied remote sensing training program is using right now. And so there's some other training that you can learn about from there. It's the main tool that we use in the lab I work in as well. And so you can see that there's a lot of different classifiers, and the key here is that we can go over here and actually start running examples and getting results pretty quickly. And so, here we see a satellite image. Right now, it's still just running the model right now in the background. But it's it really is a pretty fast way to start analyzing and getting some results right there. And so, when we're thinking about, I wanted to present random forest to you guys. I've spent a lot of time talking about a lot of other things, but it leads up to this. Yeah, exactly. So I bring up random forest because it's one of these machine learning tools that's been around for a long time. Sometimes it's called a classification and regression tree, CART. That's the other term for it. But this type of classifier works really well with data that isn't all on a 0 to 100 scale or all on the same scale. And so with random forest, you can give it elevation. You can give it some of the satellite data in there, and it will run some math and will try to find and cluster areas that are similar. And so that's where you end up with this tree metaphor, is that you start off with the full population of everything in there, and then you start branching towards those differences, usually water versus land. And then once you end up in the land area, then what's the difference between vegetated area versus bare ground? And then in the vegetated area, can you start seeing some green differences, like what's behind me, right? Like the really bright green versus more the dark green. And so it will just keep branching out and creating these different classes that it will provide back to you. And so you can see, here's an example of a classification map that was made on that satellite imagery that I just kind of popped over to. So you can see that now the next step is to investigate what these different groupings might mean that are in there. And so, that's sort of the research that you would end up doing using a random forest classifier like this, where it's just going through and looking for areas that are similar using the inputs that you put in. That could be satellite data. It could be our pictures. It could be the mosquito larvae counts could be going in there, right? So random forest is a really straightforward, approachable classifier that, like I said, just goes through and branches and groups your data together into things that hopefully are meaningful for you for your question that you're actually after. Okay, so I see a lot of questions in the chat, so I'm going to switch over there. And let me ask: is anybody have any questions about this? We'll be putting up some of these the websites and sharing this PowerPoint with you because it is more thorough. The last day of this training is actually today, so I'll make sure to share that with you because they went through how to actually start using Google's Earth Engine, how to do a random forest classification, and how to evaluate the results inside of there. And so, here with this classification, there was 94% accuracy. So they did a pretty good job with that one. So that was a very high level, quick overview of some spatial modeling.
So that was exquisite. Thank you, Peder. I think that what people are going to have questions, but would you like to just talk just a little bit about ArcGIS now and how ArcGIS has made it possible to automate the implementation of random forest on their platform?
Yeah. So I present Google's Earth Engine to you because it is much more. If you're doing remote sensing, this has almost everything you need to do that. There's still some quirks to it, but for a lot of remote sensing, Google's Earth Engine has become a very powerful platform. However, ArcGIS is another geographic information system tool platform, and that tool has been around for a tool set has been around for 40 years or so, and they also have a way to do the same sort of modeling, but within their environment. So you can see that there's a choice that has to be made. Are you going to work in Google's Earth Engine or do some things there, or work with ArcGIS and the ArcGIS Online platform? We'd be glad to talk to you about some of those considerations. But the neat thing that they have recently implemented, again, new science that is just coming out right now. They have what's called a notebook, or a Python notebook. And this allows you to implement or type in Python code to do some math, do some processing, and then you actually can run a random forest classifier in on satellite data in the same way, but in ArcGIS Online. And so by doing that, the results end up in ArcGIS Online, where you can make a story map, or where you can have a dashboard that displays the result of your mosquito habitat risk monitoring. Or if you're wanting to have a little bit more with a mobile app, that can also, these tools using the ArcGIS platform allows you to kind of build something that's integrated all together. So I wanted to highlight, these are all emerging things and methods right now. So methods are science. So if you want to learn a little bit more how to do some of this deep learning, AI, machine learning sort of thing, there's this nice resource that shows you, has some videos to walk you through how to do that on the ArcGIS platform. So I just kind of want you guys to recognize that the method is basically the same: random forest in one place, random forest in another place, and our challenge as researchers is to choose the right tool to get us to our endpoint, to our solution, right? So it's hard right now to choose, I find, and there's benefits for going with one tool versus another tool. But recognize that ultimately our goal is to try to make a model or to make a prediction. And these are two different ecosystems that get us to that point, that get us there. So, I've thrown a lot at you with this. That's what these are all about. And so, go and explore some of these tools right here. Explore what I've shown you with some of the Google Earth Engine piece of things. Keep collecting your data, because next week we are going to go back and work on getting our training data right, so that if you are a team or want to use our data to make a model, we'll have some good, robust data that we feel confident about, and that can be used for some of these as inputs into some of these tools that we've talked about today.
Great, Peder. We have got a couple questions in the chat. So while people line up to ask questions and raise their hands, one of them I thought was so interesting that I have never thought about. But Nicole said, How about rooftop gardens? How are we dealing with rooftop gardens in our work? I just
I
thought
love that. I love that one
I
because
never thought of that either. But
I've been thinking about that one a lot because literally, actually, right outside my window right now, a rooftop garden is getting replaced. It failed, and so this is a great example where we don't expect, our mental model of vegetation is not floating up 30 stories up in space. We don't expect that. And so it's not necessarily too much of a problem when we work at a 30-meter spatial scale. The first thing that we are seeing is that vegetation on top, just like the sunlight. So from one perspective, it's not that big of a problem. We just kind of end up grouping it into, it's a vegetated pixel. However, when you start changing scales, or if your purpose is different, like we're looking for all those small little islands that a mosquito could use to go from one vegetated area to another vegetated area. All of a sudden, we have to start really thinking and having our descriptions in three-dimensional space. Okay, and so really, when we start thinking about land cover, what I showed you today is wrong, right? That's just it. It's just wrong, because really we have to start thinking about what's the land cover, literally at from 0 to 1 meters off the ground. And then what is the land cover at 1 to 5 meters, and then 5 to 10 meters, 10 to 15, 10, 15 to, onwards, right? We actually have to think about that vertical structure. Mm-hmm. In the past, they've grouped those together. And so, for me, I think this is a great question that would be a great project, actually, mm-hmm. is identifying rooftop gardens. And so the strategy would be, you just go into an area and you hand digitize the rooftop gardens that you actually see, the rooftop vegetation that you actually see. And because what the classifier we would need is the vegetation with a shadow of a building, or kind of that building also going off off the side. This is a great classification and a great problem that the land cover community hasn't thought about or hasn't really done yet. So I love that. And in our definitions, Rusty, we don't have that distinction right now.
No, and that gets back to this idea of data cube, which we'll talk about later, right?
Yeah.
Not only having 4 dimensions, but also that vertical dimension is interesting. Here's another question that I just had to pose. It's from Garima, and it was like, what about artificial turf? Could you use AI to identify artificial turf?
Okay, artificial turf is another great one, because if you have one satellite, it will measure green, red, blue, or red, green, blue, and in those wavelengths, you cannot tell the difference. There's a little bit of texture difference between them, but overall, that one's going to be hard. So the only way that we can actually tell with turf is to get into the near infrared measurement, where it won't reflect any of that light, and so it will become very obvious in those near infrared, shortwave infrared light measurements. So this again is where the more spectral information you can bring in, the more you can distinguish those individual characteristics. You can even tell the depth of water by bringing in that shortwave information and getting away from the blue light, which reflects pretty harshly. But that's a really good one, because I like this. It gets into, if you show somebody, just because it's green doesn't mean it's vegetation, right? And so there is a really good data set that is a great one for projects. It's at least in the United States, 1 meter high resolution imagery. It's only color imagery. So it only has your blue, green, red light to it, but it has 1 meter pixels on it. And so there's been some counties, and the state of Vermont made a full statewide 1 meter land cover map. But they actually dealt with this issue of what do you do when a road goes underneath a tree canopy. So they actually, what they did is they made a tree canopy layer that focused just on that. And then they made an impervious surface layer that actually filled in some of those gaps and tried to fill in what was happening underneath that canopy. So, that's where that spectral information can be really valuable. And so the more of it that you can bring in, a lot of times you can get over that turf problem. That is exactly, is that really green vegetation on the roof? And so they should get carbon credits, or did they literally astroturf over the top of it and are trying to fool us into thinking that they are doing some photosynthesis and carbon capture up there?
Yep. This is great. Asil has been waiting patiently, and she has two really good questions she put in the chat. So let's give her a chance to talk about these. Asil, thank you for waiting so patiently.
Thank you. So my first question was just about like random forest iterations, because I've heard of them when I was reading a couple papers, and I was mainly wondering, like, I guess the function obviously is just because you mentioned it a little bit, was to like get more accurate and like, I guess, classification over time. But are the iterations like automatically done, or do you have to like kind of code how many iterations there are? Or are they just like automatic and finally get to like a product at the end?
Yeah, so you as the researcher get to put in how many times you prune the tree. So you build a tree, and then and it will overfit, is what we call it, right? It will do a great job on the prediction of what you put into it. That's what it does. It wants to predict what you give it. So it will do almost 100% job on that. But usually this is where an independent data set comes in. So this is where everybody else working together can help us. We'll use that to then compare how well does this independent set result? Where does it end up in this tree? And so based on that, we'll actually prune it back. And so you can set in a parameter that says, give me 10 branches, or give me 2 branches, or give me 15 branches. And a lot of times we'll literally try 15 and see what the results are, and then try 10, see what the results are, maybe try 5, see what the results are. And we'll just sort of do a little comparison about which one balances the errors, which one are we starting to not distinguish very well. And we might need to get some more training data around that. So kind of, it's a parameter right in there. How many branches you do, and how many you want to prune it back. So yeah, that's a great one. And this example makes 10 branches in it, just as kind of, they found that works kind of thing. And that's the way that most people tend to use random forest, is both as a way to evaluate your data set to see kind of where you might have biases, or where two things that might look similar might be grouping together. And you might, again, need some more data to sort of make that group more distinct. Right. So anywhere from 10 to 15 branches is kind of, it, but there's also a little bit of consideration of the number of classes you're trying to predict. And so if you have 5 classes, you probably want more than 5 branches, with it. But there's some other papers that I can definitely point you to. It's one that we've started using a lot in our lab, and we use it for land cover mapping, biomass mapping, change detection. So it's a pretty robust classifier.
Good. Can you link that paper in the chat by any chance, like later on?
I will. I definitely will. I'll add this up to our discussion board for sure. Definitely, Asil.
Oh, also, just building on what you just explained really quickly, because this was my second question, and I feel like it ties into what you just said. How can you evaluate like the accuracy of a model? I know there's like the leave one out, cross validation, leave 2 out, and then, like, I've heard from other students that they do like 80%, 20%, and like, I guess what do you feel like are the top ways and the best ways?
That's exactly right. So the best way is to have a truth data set that you are really, really confident about. Okay. But those are expensive to get, and hard to create, right? And that's the reason why they're so valuable. right? But that's what you want. And so and then you're usually right. You have kind of a whole number, usually around 1,000 to 10,000 to even a couple million samples that you use to build your model with. And so so what we're hoping to build is a large enough pool that you can do this split, and where you can take like 80% of all of our area of interest points and withhold 20% of them, and be able to do a classification where it does exactly what you said. It will go through and remove one, run through the model again and see what happens. And then it will do the same thing again with the next one and build another tree. And so this is the idea of a random forest, is it will do this thousands of times and to come up with the ones that make the most sense. And so, yes, both ways that you mentioned are the correct way that I've heard it as well. 80-20 split between the total number of samples that you have. Good. But the other way is, and this is what Rusty and I want to help and create, is a really good truth data set that we might be able to use for your model, or maybe for another team's model as well, and be able to have that. But Asil, this is the piece that we spend a lot of our time kind of going through and kind of figuring out, do I trust this data set? Do I not trust this data set? So let us know when you kind of get to that point, how many you might need kind of in the area is the other piece that kind of drives this. Is if you're working in a particular area, you need to have all your samples in that area. So, and that can limit what you end up doing as well with it. So long answer there, but you're reading the right papers and you're getting the right results.
Great. I appreciate that really intensive answer, because that's what we're going to be doing next week with the CEO. Is like, this is a very our product could end up being incredibly important in the future for exactly this kind of work. So we're going to talk more about that later. I think we have Imran has been waiting a long time. Maybe that'll be our last question today. If you have more questions, of course, put them in the chat that we have the discussion thread online, and we'll make sure that Peder gets to them. Imran, do you want to ask the last question?
Sure. Thank you so much. I wanted to direct this question primarily to you, Dr. Lowe, and Mr. Nelson, since I know that you both work with data that results from remote sensing quite often. And I've been pondering about this for a while. I know that there might be small impurities in the data that you collect from the remote sensing from those satellites. But one of the impurities that I kind of figured might exist, I don't know the extent to how precise each measurement can be when it comes to sensing ground data, but are people on the ground ever counted as impurities? Like, I wonder if the light emitted from the satellite ever reflects off of an individual on the ground and ends up affecting the data.
That has to be a Peder question. I can't answer that. So good. Go ahead, Peder.
Yeah. Overall, no, but this is some people have run some experiments with this where they've actually tried to change the color of the pixel. If you have a big crowd of people, yeah, it's definitely going to affect the light. We have to account for this thing called the Bi-Directional radiation distribution function. So this is basically like if you try to actually track that sunlight through all of the different reflections and absorptions that it does in an area, definitely, people are reflecting, their clothes are reflecting, the ground around them is reflecting and absorbing. And so, yeah, Imran, like you would expect it to be probably darker in some wavelengths. It might be brighter in some other wavelengths. And then if the people weren't there, just like those clouds, actually, you would actually see the ground underneath it. And so that would be a way that we could account and actually quantify the background color of that pixel versus what the people actually put into it. And we could possibly quantify that the density of people in that area based off of this in a similar way as what we would do with trees. The more dense trees are, they bounce and reflect the light in a particular way. People would do kind of the same kind of thing. And that's, the interesting part about remote sensing, but usually going back to the sampling piece right at the very beginning, we usually don't know when people are at those locations. And so in our model, it becomes part of our error that we just can't quantify. We can't quite understand exactly why the light is doing this thing here. But it, like what Rusty mentioned, if we knew Burning Man was happening or that there was a huge gathering of people in this particular location at that time, we might be able to create a model that accounts for the people on that pixel. And I just love that question, Imran, because as we start getting more high resolution imagery like that, this is a way you can quantify crowd size. And it's one reason to have a highly reflective surface like white tarps, because then you can actually, you have dark people walking across those. And the more dark people you have going across, the more, the easier it is to count them and to get crowd sizes. So there is an actual application that I was able to walk through from your question to how people use this in remote sensing in exactly that way. So I appreciate that, Imran. That was a great question for me to kind of ponder on.
Awesome. Thank you so much for the insight, Mr. Nelson. I haven't thought of it from that perspective before.
Yeah, definitely.
The questions, I've written this twice. I can't believe these great questions you guys are coming up with. So here is, you've got your reading this week. It's a really good paper that will put a lot of some of the more basic ideas about modeling. It'll put that in perspective. You'll have Mike Wimberly's video that will be in the calendar for this space. It's about 40 minutes long, where he talks exactly about how he does use random forest in a mosquito project, which I think is going to be a very nice demonstration. But what I really want to stress today is the fact that we're now beginning to think about groups and projects. And in the discussion board this week, there is a special, oh, cool. I got to read that. Okay. I don't want to read that. Okay, I lost my thought because I got really excited about Burning Man. Okay, so Mike Wimberly's video will be, it is not yet, but it will be in the calendar for today, because we had hoped to show it, but once we sort of went over yesterday what we're going to be talking about, we didn't think we'd have time we didn't want to make you sit here for 2 hours and 15 minutes. That's too long. That's like my day, and that's no fun. But back to the discussion board, we are asking you to brainstorm. You've already been brainstorming today some of the really great ideas, and you can see that, just saying, oh, well, what about Burning Man? That could be a research project, right? I mean, it just like taking these sort of random thoughts and sort of beginning to massage them a little bit. So what we're asking you to do is to realize that nobody is judging your crazy ideas, and the crazier the better, as far as I'm concerned, because that is where genius comes from. Am I right?
Exactly.
And so put up your sort of like your aspirational. If you got 6 years of PhD funding, what could you do with this data? What could you do? I know we only have 3.5 weeks, so we have to cut that down a bit. But go ahead, put your ideas out. We're asking you to read other people's ideas and comment on them and help them get refined a little bit into other ideas. Both Peder and I will read, and Cassie, and also I hope Becky, I don't know, I haven't asked her yet, but we will all be looking at this discussion thread and adding our 2 cents to sort of help this process of coming up with ideas. So Peder doesn't have a lot of time on the weekend, but certainly by Monday, you'll be able to look at some of those, right, Peder?
You got it.
Right. So that's our plan. And then from that, we'll begin to We're going to do something to help people find a group that they're interested in working with. And then we can begin to start nailing down what we're going to do for the last 3 weeks of this opportunity, which is really the research piece. So I think that is all I need to say. Does anyone else have any announcements, Cassie or Peder?
No, hopefully this was stimulating and got people thinking about, modeling a little bit more. The particulars about data. We can get into those as you get there. But be thinking big and let us know what you want to be doing, and hopefully we can help make that happen, at least in terms of the research.
Yeah, that's great. Cassie, do you have any announcements?
I don't at this time, but I think we're going to start talking about putting all the pieces together of their research and what's required for down the road pretty soon.
Yeah, we'll definitely try and make that available to you next week, just so you know kind of what the outcomes are going to be. But basically, the broad line is that everybody's going to do a poster where you describe the research that you've done, and then we'll ask you to do a short 5-minute group presentation where you just describe what you have done during your research. And that is really one of the funnest parts of this project is to listen to everybody's great ideas. So thanks so much, Grima. There is a special discussion post this week that says brainstorming ideas. So that's where that goes. So please put your ideas, please read, I would say at least 5 other ideas and add your contributions to it. You might find something you really want to do instead of your idea. You might be able to help someone else refine their idea. Your ideas can be anything from building on the work that you've done with traps to some of these AI things. So really the sky is the limit. And here's the last thing that Peder reminded me to say today is that, okay, maybe you're interested in AI and you have no experience, right? Should they not go on to that? Should they not be part of that team, Peder?
Oh, they should definitely be part of that team.
Yeah.
That's the best way to learn. And not only that, but one of the things that I was thinking about and reminding myself is we need science storytellers, people who can communicate what that team is doing. And so even if you're not the expert on that team, there's always that role to play. Documenting the data, helping people to understand what they're doing, and being that translator between sometimes the what I get called the hyper nerd to the general public and everybody else, right? And so even think about that as something that you can explore here with this. And so don't be intimidated by those people who are asking all about modeling and random forest and some of those particulars. If you're just starting to explore this area and are curious about it, use this as a great time to get to know some other people and to maybe help the rest of us understand that through your own learning with that. So I just wanted to highlight that science communication piece is a really important one as well. And as we were highlighting, this is how you go to conferences. This is how you get other people to use your work. And so that science communication piece can be a really important part of a project, whether it's successful or not.
Right. And just as a last little bit, because I do not want to go longer than an hour and a half, we got 2 minutes. Just want to say when I was in graduate school, I learned more from my peers who were doing cool things than any professor I had. And I learned by just working with them. It's like, oh, I don't know how to count varves. Who may count some varves for you? And we can use that to determine, when this event happened, in prehistory, all kinds of stuff. So anyway, thank you so much for your mostly undivided attention today. Peder, thank you so much for a really interesting presentation. We really appreciate it. And we look forward to interacting with you on the discussion board. And Peder, you're also going to put up some one-on-one hours for next week to talk about projects, right?
Exactly. Projects, remote sensing, coding, anything that you want to talk about. If you haven't had a chance to get a hold of Rusty yet, look for some times to meet up with me.
Right. And also, you could either do one-on-ones, or if you've got like a little group already that are thinking about something, come as a group and talk about your ideas.
Yep.
Okay, that's it. Thank you for a great week. We'll see some of you this evening at 6 p.m. CT for Meet Up and Do Science.